Topic is a little bit unusual for us. And also where this fluid, which is way too large for the standard elevated, blame it on the registrar. They screwed up. That's the other thing. And as usual, the registrar screwed up, so we ended up here. I think on last week, of the year, we ended up. That will be here. Okay, so it's a pleasure with Xinting. I don't know if that's enough.
Yeah, more or less.
For the Department of Physics and Astronomy at the University of Texas, San Antonio. Xinting was a student in space physics at USDC, Hefe, and then got the PhD from Hopkins. He applied by science. She was a principal doctor like after and then since 2023, she's a professor at she's of course a primary scientist, and in particular she studies what happens on the ground and then has she's not that strong. Doesn't telescope, or she has cases in the farm. So thank you.
Thanks for the invitation. So like Georgia said, it may not be a Euro center about physics, but today I'd like to talk to you guys about the topic is usually I feel like most people imagine they start doing series and transition to the lab, but for me it's actually opposite. But today I'd like to talk to you about the work we've been doing on understanding the nature of some of the really weird, maybe not so weird exoplanets out there. And hopefully at the end of this talk, you can feel like you can talk to your friends a little bit better about some recent news story about we may have detected alien life on other exoplanets, and you can explain to them about those stories. All right. I don't know if you guys seen this. Has anybody seen this news story? Yes. So it was kind of I think 4 weeks ago. There's a paper published on Archive and Stanford later on SJ. And then there's a person, this is a guy named Madhu. He claimed he has detected marine life on this exoplanet with a weird name called K218b. So it's pretty much the Kepler mission, the second phase of Kepler mission, the 18th planet it discovered. And he says, based on the title, it's more habitable than Earth, so see what's better. Okay, so that's what I think I was brought here to talk about pretty much. And it's all because of the culprits. It's pretty much because of the spectrum that was taken by the James Webb Telescope. And they're discovering molecules they called dimethyl sulfide, DMS, and then dimethyl disulfide, so DMDS. And they're claiming these as the so-called biosignatures indicating life on the planet. Okay? So that's, I think, why I was brought here. At least that's what I think. And today I'm going to start with this journey, but not on this planet quite yet, but we're going to get there. I want you guys to get excited actually about this other planetary body in the solar system called Titan. So that's where my journey started in grad school and everything. And Titan is still to date my favorite planetary body in the solar system. So how many of you have heard of Titan? Oh my God, you guys are so educated. I love you guys already. So Titan is the largest moon of Saturn. Okay, and in the next few slides, I'm going to try to convince you guys. Titan is the most Earth-like planetary body in the solar system, whether you believe it or not. Okay, so you might already want to argue with me and be like, okay, Titan is much smaller compared to Earth, right? So it's actually bigger than our moon, and it's actually a little bit bigger than Mercury, but it's still much smaller than Earth, so the gravity is a lot less. Okay, but now we start with the similarities. So Titan actually has a very Earth-like atmosphere full of nitrogen. Okay, so Titan's atmosphere is very nice. There is about 95 to 98% nitrogen, and it's a 1.5 bar atmosphere. So it's actually 1.5 times thicker than Earth's atmosphere. Okay, and you're like, okay, Earth doesn't look like a giant yellow ball, right? But so what is happening here? So we're seeing this yellow stuff on Titan. It's actually these aerosols, tiny aerosols forming the atmosphere. So they form these thick haze layers. So if you've ever been to LA, they're very similar to like the smog you see because of all the pollution happening over there. So there's one ingredient I'm trying to actually hide from you guys. So other than N2, Titan's atmosphere is actually full of this other ingredient that's super important. That's methane. So Titan's atmosphere is about 2 to 5% of methane, depending on where you look. And then because of this methane, there are actually some very amazing chemistry happening in Titan, in Titan's atmosphere. So we can have energetic particles coming from Saturn's magnetosphere, and also the sun's UV photons can really shoot up this chemistry by dissociating these molecules. We start with making very simple gas-based organic molecules, and to date, we know this chemistry happening because we've seen lots of these molecules forming. So ground-based and space-based observations have tell us there's so many very cool organic chemistry happening in the atmosphere, and these are all the molecules we have seen to date already. And we also know that these simple stuff can further polymerize and coagulate to form more complex organic molecules, and then they can aggregate to form bigger stuff, so that about micron size before they fall to the surface. So these solid haze particles will be forming these like yellow stuff we're seeing pretty much in Titan's atmosphere. So this process keeps happening in Titan's atmosphere, making the haze layers. So you have to say, well, even though Titan, our Earth's atmosphere currently do not have much methane, but there are some resemblance actually between Titan and Earth before any life arises. Actually, people even have oxygen. So if you look at these two planetary bodies, you realize, okay, on Earth, before the life arises, we believe at some point Earth's atmosphere is actually quite reducing, which means it could have a lot of methane. And then Earth is even closer to the sun compared to Titan, right? And it's also subject to lots of high energy particles and UV radiation. And we believe Earth's atmosphere before life arises actually makes a lot of these hazes that are very organic rich. So people have been trying to answer this question, hey, how does life even arise on Earth, right? So I would not say it's a solved problem, but at least people kind of agree on, these photochemically made organics could at least maybe serve as an initial organic matter for life to start. So it's like the soup, you have all the ingredients for life to start there. So that's why we think Titan is actually pretty similar to Earth before life started, and it might provide some clues for how Earth could be like before life gets started there. But anyways, we actually get to see Titan pretty well. We sent a whole mission there called the Cassini-Huygens mission from 2004 and 2017, and we started to take very amazing images of Titan. And to look at Titan, you have to go through the thick haze layers, which means you can't really use visible wavelengths because visible only lets you see the big yellow sphere. And so this is actually some radar images, one taken for Earth and one taken for Titan, because we have to use radar to penetrate the thick haze layers. And now I'm gonna make you guys think about this. So which one do you think is Earth? Which one do you think is Titan? Now let you guys think about this and then vote. So and obviously these features, this is a lake we're looking at using radar. Okay. All right, let's vote. So how many people think on the left is Earth? Raise your hand. All right, how many people think on the right is Earth? Raise your hand. Seriously, you guys. Half again, not so bad. Hey, there we go. They're pretty sure, right? So we're seeing some lakes on Titan. But isn't it kind of peculiar if you compare the temperature between the two planetary bodies? You're like, okay, do you guys know what lakes are made of on Earth? Okay, you said yes, water. On Titan, how could water still be liquid, right? So actually, all the stuff that's around it, like the white patches, that's main rock and radar, water, but they're in ice. Water is like a rock, and it's pretty much forming ice. So the lake we're seeing here is actually made of liquid methane. Okay. So because, and I highlighted this temperature 94 Kelvin because it's very close to methane's triple point. So methane can really transform into a liquid, and again, sometimes a solid on Titan. That's why we have a methane cycle on Titan. It's a Titan pretty cool, you guys. So that's one of the resemblance based on geology, guys. And we all know that because of this formation that NASA tens of years ago. All right, so the next thing, and I just cannot not show you guys this image. So this is taken by one of the mission component called the Huygens. So Huygens is a land that we sent to Titan. So we actually landed on Titan. It's a 1-point land, and this is actually taken by Huygens on the way of the descent. You can see this like panels on Titan. Isn't that pretty cool? So all made of liquid methane. Very Earth looking. Okay. And now I'm gonna bring you to some of the stuff actually I'm pretty familiar with. So this is showing you comparison between Earth and Titan, but different geologic feature called dunes. So I'm not gonna make you do the guessing game again because it's quite obvious. You're looking at the visible image on the top, right? On the top is Earth. So we also see these dunes on Titan. So they look like these very long features in radar. Initially, people don't know what they are. They just call them the cat scratches. But anyways, the dunes on Titan actually resembles dunes we see on Earth. But the material is actually made of the dunes is very different. Because on Earth, if you go to like a sand field, all right, we're pretty much playing with these like silicate sand that's like made of quartz, okay? But on Titan, silicate is not a bad rock. And based on what we've seen with continuing equations using infrared data, we know this sand is actually very organic rich. So we think the sand is probably originated from the atmosphere, like, it's like the haze settling down and then making the sand we see on Titan. So it's very different material. So I would say this is the perfect place to give this talk because I was here, in this area, just down the road, 10 minutes from here, about like 11 years ago. So that's my first project ever, was actually working in this really cool facility called the Titan Internal at NASA Ames. So just some humans with scale. As a first year grad student, I was like super excited. Brand new facility. We're trying to study how the dune forms on Titan's surface. Okay. And on my day one, walking through the lab, super excited to get started. But I was immediately quite disappointed when we started experiments. Because I realized, the materials we put in the Titan wind tunnel actually grounded water shells and grounded instant coffee to simulate the sand of Titan. This is quite peculiar because, I studied Titan, I read some literature when I was first year grad student already. I know that there's photochemistry happening in Titan's atmosphere. They're making some complex organic molecules, and these things we believe fall on Titan's surface, and they make up the organic sand on the surface. So, well, water shells and instant coffee, they're all organic. So we don't really think they're the same organics as the organics on Titan. So here comes my quest. I was like, you know what? I think I can find a better material we can use in Titan wind tunnel for our experiments. But, well, you guys probably might already know this, but to date, we do not have a sample returned from Titan yet. So, like, how do we actually even simulate Titan sand, right? That's organic rich. So, while we're laboratory scientists, just like most of you here who study in the laboratory, so that's, how about we mimic Titan's environment in a laboratory on Earth by doing some simulation experiments? And the idea is very simple, so that's actually invented by Carl Sagan and Ulrich Perry. So how about you start with some gas mixture that mimics Titan's atmosphere composition, and you expose a gas mixture to some energy source to mimic the energetic processes in Titan's upper atmosphere. For example, you can use a UV lamp to simulate UV photon coming from the sun, or this energy source called cold plasma to simulate some energetic environments from Saturn's magnetosphere, like the energetic particles. And then you let the reaction go on for a few days, and you make this final material that's named by the two inventors called solene. So solene means Greek, being Greek, muddy, pretty much. And that's kind of how, if you play with the material, that's how you feel, but they're pretty sticky. But basically, I've done this as a grad student, and you can see the color of the haze we made in the lab is pretty close to like this yellowish stuff that exists in Titan's atmosphere, right? Anyways, I was like, you know what? I happen to be a lab that makes solene, so my colleague Charlie, he's now a professor at USTC actually. He actually built the setup at Hawkins to generate paste. And I was like, Chad, you know what? Let's make some samples together. Let's use it for the Titan wind tunnel. So we decided to make some paste. And then it took us about like 3 days. And then we had to scrape the whole chamber with all the gas mixture. And after all that scraping, we run experiment again for like whole 3 days nonstop for 72 hours. This is how much material I collected. So I got about like few hundred milligrams of samples. Okay. And do you guys remember the scale of the wind tunnel? It's like with a human size. So actually each turn we need about 2 to 3 kilograms of materials to run it to study like dunes. And also, do you actually want to put this much material in a Titan material like Zoling? Given that what happened to Carl Sagan. So anyways, so I was reaching kind of a dilemma point at my PhD. I was like, man, like I don't know what to do because here's the situation we have. We know that there are dunes on Titan, right? And we know that dunes exist in different places. It exists on Earth, on Titan, and the wind tunnel. And there are all different kind of materials there. We have porous sand for dunes on Earth. We have organics for dunes on Titan. And we have water shells and instant coffee for the Titan wind tunnel. So I was like, you know what? How about we figure out some properties that are important for dune formation for all these different materials, and then we just look into whether these properties exist, and then maybe we can then do some corrections to the Titan wind tunnel data to make it more realistic for Titan. So that's what I did. So I started looking to literature and figure out what properties matters for dune formation and sand transport. So here are the properties that I found. So for example, the surface property, which is the stickiness, will govern how sand will be moved, right? If your sand is more sticky, you need more weight to mobilize it. And the electrical properties, like when sand are being like rubbed upon each other, right? They might generate some triboelectric charges. And those charges would affect how sediment further transport. So that's kind of important. And mechanical property matters too, because when your sand is moved upon each other, they collide on each other, they abrade each other. So how strong your sand is also very important, governing their, like how long they can be sustained and their particle size will be changed and all of that. So I looked in the literature, these are the properties that matters. Well, none of that actually existed for the Titan materials. So that's how I can get a PhD, you guys. I actually measured all of these properties. So to do that is not very simple because we don't produce a lot of materials. So I actually introduced some of these pretty well-known techniques in physics, but not so much in planetary science at the time, to like study these materials. For example, I can glue, like I can coat a single grain with my material, the Titan Zoling, and then I can measure their stickiness, whether they charge each other or not, using atomic force microscopy, and I use this technique called the nanoindentation to measure the mechanical properties. But the basic idea is we found the Titan sand is very different compared to Earth sand. And nice thing about each of these measurements is that they all have direct implications for understanding dune formation and sediment transport on Titan, which is pretty cool. So I defended my PhD on June 2019, which is pretty good. I got my PhD. And then the even better news is about a month later, NASA announced, so NASA selected the mission actually to go back to a planetary body, and they choose, Titan again. And I think this is not one of, this is the coolest mission NASA is ever gonna send to another planetary body. It's the mission is called Dragonfly. So we're gonna send a drone, you guys. We're gonna send a drone to Titan, which is pretty cool. And guess where it's gonna land? It's gonna land right in the place where I did my PhD. It's like 2034. So yeah, it's like, man, I'm gonna have to drop the rest of till 2034 at least. That's what I do. So that's Titan. And then I started my postdoc at UC Santa Cruz. I was still kind of continuing some of my Titan work. Well, I was at Hawkins, Johns Hopkins. So you ever been to Maryland? It can get quite hot and humid in the summer, right? And we make these materials with methane and nitrogen, which does not contain oxygen, right? And I always do experiments. I always went to the material science department, and they never have any environmental control and all these measurements. I've been always wondering, hey, would any oxygen or water vapor in the atmosphere affect any of my measurements, right? introducing the unwanted oxygen to my sample and affecting my material quality translation. So, I kind of was curious about this, and I hired some students when I was a postdoc at UC Santa Cruz, which is down the road. You can grab the 17. But I didn't have any money. It was a postdoc, right? So actually, my postdoc advisor got me a lab space, but I was able to do some very cheap stuff using Home Depot to perform some of the tests. Basically, we made some of the samples, but then we made some never touch air, and we measured some properties, and then we exposed some sample in air to be measured property again. So we choose a very simple property measure called surface energy. You guys might have heard of this physical properties. It's pretty much using very simple measurement called the contact angle goniometry. So we've done it for like a sample that never touched air. We've measured it in Earth atmosphere in the little glove box that built, and then we put a sample exposed in Earth's atmosphere, and we measure the property again. So the surface energy is pretty much determining how sticky your material is. And the higher the surface energy means material is more sticky. And the other nice thing is it can be separated into two components called the dispersive and the polar component. And that kind of tells you something about the bulk chemical composition. For example, if your material is more polar, have a higher polar component, it might have more like polar bonded material like molecules. I would say it's in general more polar in the structure. But basically what that tells you is, well, if you expose those samples in air, it's gonna change really your chemistry laws, because you can see the polar components like increase and the dispersive component decrease. So we know that we don't really want to do any of our translation on Earth's atmosphere. So this is what my big part of what my lab is about. So I wanted to build a facility to actually measure lots of material properties of different materials not in Earth's atmosphere, but in controlled environments. That's kind of what my lab is about, and we designed the logo first. Well, before we do the lab, actually, to advertise this, I have a planetary material translation facility. So basically, we do all of our translation in Earth atmosphere. So this is actually our new instrument that's recently built that operates constantly less than 0.5 ppm of water and oxygen. And then this is the optical ellipsometry system that can measure optical properties of material from the UV to the infrared. So you guys know, like, why do we hire this person to talk about Titan? How is this relevant to K2BP? I'm gonna get there. So this is part of what I did during my postdoc, and then as a faculty, we do lots of planetary material research for all these different kinds of materials. So if you're interested in any of these materials, please talk to me. But the other part of my postdoc, well, or at least when I got the postdoc fellowship, I was actually quite intrigued by this very new booming field exoplanet science, right? So I took a screenshot of the NASA exoplanet archive last night, and today it's kind of amazing. You guys, we already see detected almost 6,000 exoplanets, right? So like if you talk to some of my Earth fellows, like they kind of don't like this field, but I mean, like you just cannot ignore it. There are these exoplanets out there, right? So I was quite intrigued by this field, and I started wanting to do that as a postdoc. And then the James Webb Telescope is really exciting for us because, when I just entered this field, I've seen there are still mostly astronomers working on it, which means astronomers measure very basic properties of these planets. First, whether they exist or not. And then second, they measure stuff like their size, how big it is, and then their mass. That's pretty much all we know about these planets. But with the James Webb Space Telescope, which is pretty much enabling us to look at the atmospheric composition of all these exoplanets, we're kind of entering this new era. Like, astronomers, do they understand atmospheric physics and chemistry? Well, not really, I guess. That's why, so the idea is, well, we could, use some help from people who know this kind of knowledge, from people who study solar system bodies, for example. I guess that's how I become useful. And I was quite intrigued by this problem. So, like 2019, we kind of already have a good idea. We have basically 3,000 exoplanets detected already, to the point people can look at this demographics. Okay. So, for example, for this figure, on the x-axis, we're showing like planet size, and on the y-axis, we can look at how often they occur. Okay. And it's very interesting that you guys, the most popular types of exoplanets discovered actually have sizes between Earth and Neptune. You can see that, right? So that's quite interesting. And there are lots of people arguing, okay, what are the nature of these kind of intermediate-sized exoplanets? And some people think, well, these planets are either kind of Earth-like or Neptune-like, or maybe some other people argue, well, maybe they're their own kind of worlds that's very different from Earth and Neptune. And I kind of looked into this problem, it's like, isn't this pretty easy to figure out? I was like, hey, we know something about the solar system planets, right? So I was thinking, well, if you figure out how thick the atmosphere is for these intermediate-sized exoplanets and the surface condition, like the pressure and the temperature of the surface condition, like you can categorize it, right? Because we know that for the solar system, the terrestrial planets tend to have pretty thin atmospheres, right? So we're talking about atmospheric pressure, maybe like less than 100 bar, with Venus being the extreme case, right? And if we look at the giant planets in the solar system, like Neptune, Uranus, and Jupiter and Saturn, they tend to have very thick atmospheres. So if you were to define a surface, it's going to be very thick. So at least like 1,000 bar, right? Like very, very thick atmosphere. And the surface, whichever boundary you define, the liquid to gas transition or whatever, it has to be like over 1,000 bar. And I was like, if we can figure out the surface condition for these exoplanets, we can figure out their nature. Well, it turns out it's not very easy to do. So the James Webb Space Telescope, or the Hubble Space Telescope, or this European mission called Ariel, they're all using this technique called the transit technique to look at, and they're very good at looking at the composition of these exoplanet atmospheres. So how that works is basically, well, if you have the stars like of those exoplanets passing, through the atmosphere, and if you have some molecules in the atmosphere, they're actually going to make the atmosphere look a little bit bigger. So you're going to measure bigger radius at those wavelengths, these gases also. So, it's a little bit different than spectroscopy where we see dips. So we're seeing, whenever you see like a feature for exoplanet atmosphere, it's actually going to be like a bump. So that's you can kind of measure how big it is to figure out the composition. For example, water absorbed at 1.4 microns. So you're going to see a bigger atmosphere because how transit spectroscopy geometry works. However, this technique is great at constraining what is in the atmosphere if you do it for like a big enough wavelength. But sometimes we're seeing spectra like this because there's stuff exists in the atmosphere like clouds and haze, will make things a little bit worse. But overall, it's not very good to look at the surface, where the surface is, and what is the surface condition. Well, there's another technique called direct imaging. So that's actually a very, intuitive technique. The idea is, well, if you're somehow able to block the stars, like all the light coming from the star, right? You can pretty much just see the planets orbiting around it. Then you can directly see the emission coming from the planet. And the emission is actually quite sensitive to the surface condition. You might get to know the surface temperature pressure. But pretty much this technique is ideally very cool, but it's actually technically very challenging because it's very hard to completely pull off the light from the star. There's diffraction, there's like other stuff happening. It's very hard. So currently the direct imaging community, we're pretty much looking at a planet that's like 3 times Jupiter size, like not like say like 3 times Earth size. So pretty much have to wait at least like 20, 30 years until the next generation space telescopes become available. Like for example, the Habitable the observatory. So basic idea is, well, we can't directly detect the surface condition for these intermediate-sized exoplanets. So what do we do now, right? Like with data from the James Webb Telescope. I was like, I was a solar system person. And I was like, how about we use some knowledge coming from the solar system science and help us figure out. So in this case, I just choose 2 planets in the solar system, or 2 planetary bodies, because it's not like planets. One with a thick atmosphere and a deep surface, which is Jupiter here. And I choose another planet. Of course, I choose Titan. That's why I spent so much time talking about Titan, which has the same atmosphere and a shallow surface. And I want to see what's different between these 2 planets, right? So I found out actually there are very different things happening between these 2 species of ammonia and methane. Well, actually both species experience photochemistry in the upper atmosphere because every planet has an upper atmosphere that's being exposed to like energetic processes, right? So we know that ammonia and methane in the upper atmosphere will be dissociated photochemically to form stuff like ammonia, like for example nitrogen and hydrocarbons. But for Jupiter's case, because the atmosphere is so thick, right? After you form these nitrogen and the hydrocarbons in the upper atmosphere, these photochemical products actually go to the deeper, harder part of the atmosphere. So transport and diffusion, and they will get it eventually because they're lighter than the background hydrogen atmosphere. And because they can get there and it's very hot and deep there. So and there's a lot of hydrogen. Pressure is very high. These photochemical products actually naturally transition back to the parent molecule, which is ammonia and methane. And these reformed ammonia and methane actually diffuse back up to replenish the ones that are being kind of dissociated in the upper atmosphere. So eventually, we expect to see loss of ammonia and methane in like Jupiter's atmosphere. But for Titan's case, pretty much this reaction happens, and because the atmosphere is so thin, pretty much this just keeps going on. Just the photochemically formed nitrogen and the hydrocarbons have really nowhere to go. So nitrogen actually fills up the whole atmosphere. And that's why we believe that's why Titan has a 95% nitrogen atmosphere. And the hydrocarbons has nowhere to go but to be deposited on Titan's surface. And you guys, that's why I get to study the data sometime for 5 years. So the hydrocarbons formed by photochemistry just pretty much just start to fill up the surface. But eventually you can see this cycle just keeps going, and eventually we see it's gonna deplete the amount of ammonia and methane in the atmosphere. So we're gonna expect to see depleted amount of ammonia and methane in Titan's atmosphere. So now we have this kind of dichotomy, right? You know, a planet with a thick atmosphere with a lot of ammonia and methane, and a planet with a thin atmosphere with depleted amount of ammonia and methane. We're just wondering, hey, you know, can we use the abundances of species within the upper atmosphere to guide us to figure out what is the lower boundary condition? How can we use that to figure out what is the surface condition of exoplanets? So, well, you can't, this is kind of an idea ahead, but we did actually test this idea. So that was 2020 during the pandemic. And you know, like I was just browsing literature, like I just need to find a target to choose. And here we go. I found K28 and K. So at the time, there are some observations from the Hubble Space Telescope. And if you look at the size, it's in between Earth and Neptune. And the temperature is pretty good. I was like, let's go for that. So that's how I started doing work out K28 and K. So we modeled kind of the chemical composition, the equilibrium chemical composition first. So on the left, we show that for ammonia, and on the right, we show it for methane. So on the x-axis, we have the mixing ratio. So, you know, like for some people find it weird, but mixing ratio, if you more towards the right, you have more of these species, and if you more towards the left, you have less of these species. We make these balls, we call them spaghetti balls, but that's just what they're called. On the y-axis, we have pressure. So let's look at ammonia first. So on the dashed line shows if we only have chemical equilibrium, and the thick gray line shows if we assume like a thick atmosphere and a deep surface. That's how much ammonia we can predict. And now, how about let's add a 100-bar surface? As you can see, ammonia abundance doesn't do anything for a 100-bar surface. But if we have a 10-bar surface, you can start to see, oh, ammonia abundance starts to actually drop. And then if we have even a thinner surface, like a 1-bar surface, ammonia abundance further drops, which is actually very good. And we can do the same experiment for methane. We add a 100-bar surface, nothing changed. And let's do a 10-bar surface. Well, actually, this is a little bit different than ammonia. So for 10-bar surface, the methane abundance doesn't really change until you start having a 1-bar surface. Methane starts to actually become a little bit less. So this is actually very good, exactly like what predicted. We predict less methane and less ammonia, the thinner the surface it is. And the other good thing is that because it seems like these carbon and nitrogen species have different responses to different surface conditions, we made this like flowchart to guide the astronomers what they can do when they have these observations of the atmosphere composition. And you can not only, so the idea is you can not only tell, how deep the surface is, like the surface pressure, but you can kind of tell whether you have a deep surface or intermediate surface or shallow surface, for example. And we even hired a undergrad to make some predictions for us with the GIS data. So you can see like 1 bar surface versus a deep surface and lots of differences in the spectral features we can see with James Webb. So that's all pretty good. And then you guys data came. First data came 2023. Okay, so this is spectra. That's what every series want to see. They want to see a real spectra to test their series. What do we see here? So we see certain features of methane, and then CO2. So that's pretty much the main conclusion. So 1% methane, 1% CO2. We did not see any ammonia. We did not see CO. And while they claim the 1 sigma detection of DMS, which I'm gonna get to later, but at the time, we're pretty much, that's 2 weeks. For astronomy, I think typically we want a 3 sigma detection to get a solid detection. So we treat the first 4 species, I would say more like rigorously. And since my paper was published 2021, a lot of people have looked at the surface, how the surface affects the atmosphere composition. For example, I did a simple case with like a Teflon surface, so the surface doesn't have any interaction with the atmosphere. Some people look at, okay, what if the surface is an ocean, right? Because the ocean can absorb some of the species or react with some of the surface. And some people look at, okay, what if there's magma ocean underneath? How does that affect the atmosphere? So obviously, we tested a bunch of different cases, and unfortunately, the series a little bit disappointed. None of these, at least the first situation, 3 situations, we cannot explain why we see 1% methane and 1% CO2. For the sea atmosphere case, we don't expect much CO2 at all. Actually, we probably predict only 1 ppm of methane. And then for the ocean case, again, we predict 1 ppm of methane, not 1%. And for the deep atmosphere case, we do not predict that much CO2. So none of these are very good. The Habitable ocean one was a little bit tricky, so I was actually talking to Laura about that. But I think we cannot explain why there's no CO. So actually, as you can see, we're left with one situation, which is actually kind of a peculiar situation that some climate model actually suggested. So if this atmosphere is hydrogen rich, right, and it has some water, we think hydrogen is actually a very good greenhouse gas. And we think they're going to actually cause the climate overall to become a little bit hotter over time. So we believe it's going to get so hot that water actually exceeds its critical point to become this in this phase space called supercritical, right? So if you guys remember like the phase diagram of water, once you get beyond the critical point, water becomes supercritical, means it starts to become miscible. It's like a gas and a liquid, but miscible, you cannot distinguish each other. So that was the untested scenario at the time. So I was like, I want to continue working on this, right? But this is kind of a crazy problem. So we have this miscible supercritical water and hydrogen mixture on the bottom. We want to figure out, okay, how does key carbon and nitrogen species partition in this ocean? And then how does that affect what we see in the atmosphere? And this is like actually pretty hard to do. And I was kind of a little bit convinced by some people need to do molecular dynamics simulations. And you get together in the lab first. I don't know how to do molecular dynamics simulation. I didn't quite like the idea. But anyways, I get to chat with my colleague, Chris Klein. So Chris Klein, he's like icy moon, like an Earth geochemist, okay? And he introduced me, he said, you don't need molecular dynamic simulation. We actually have a model in the Earth community that can maybe help you. So he introduced me to this model called the deep Earth waterfall, okay? So you guys know that we have plate tectonics on Earth, yes? You guys heard of plate tectonics, right? So basically we think of Earth, we have these oceanic plates. They are being subducted underneath the continental plate all the time. So that's pretty much bringing a lot of water-rich material and going to very high temperature and pressure. And obviously, actually, people who study Earth geochemistry, they're very interested in how these water-rich, like how the volatiles in this water-rich stuff like ocean crust, when they're subducted and being experienced like high pressure and temperature, how do the volatiles position under those high temperature pressures? So they're actually able to build this model that can apply to study chemistry up to 60 kilobar and 1200 degrees Celsius. So that's actually that's pretty good for us to study how the supercritical ocean chemistry works. So that's what my student did. By the way, this model was developed by this guy, Dimitri, who was pretty much in my department, and he was blaming me later for not taking his geochemistry class when I was a grad student. So you guys, you never know what you're going to miss during grad school, right? You know, I was regretting not taking his class, but now I'm using his model. But anyways, so do not miss anything in grad school. Try to take as many classes as possible. Talk to all the professors you can. But I found that's pretty cool. So that's actually how we figured out Enceladus, which is a moon of Saturn, has a hydrothermal fluids. Because we never get to measure directly the hydrothermal fluids. All we know is actually there are plumes coming from inside the South Pole. We actually know the composition of the plume, but that's how we actually we use kind of similar stuff. We know the plume and we're able to back out what is the condition of the fluids that's ejecting these plumes. And we get to know that they're hydrothermal. So, you know, using similar models. So actually this kind of exercise that they've done for the planet as well. So that's kind of what we're doing, but we're doing in a forward approach. So say we start with some volatiles in the supercritical fluid, and how that affect, what we see affect this. So we're able to use this deep earthwork model to model that. So that's what worked on by the student, that's published at the end of 2024. So pretty much we study the speciation of two important species, methane and CO2. So those are the most important discoveries of Webb. So we first model the composition of the ocean in aqueously in the supercritical ocean, and then we're able to use some dissolution laws, the Henry's law, to figure out how much would it be, for these two species, their ratios in the atmosphere. And basically, the gray region shows you the geography observed methane and CO2 ratio, okay? And that can immediately give us actually a lower limit of the ocean temperature. So we found that if there is an ocean, it has to be at least 700 degree Kelvin. So that's pretty hot, and it's definitely a supercritical ocean. So that makes us say, well, is this a hydrothermal void? But anyways, we can do the same exercise for the CO and CO2 ratio, and that leads us to find ocean temperature about, well, it has to be less than 1100 Kelvin to fit to kind of explain what's the CO2 upper limit. So basically, from Cindy's work, we're able to constrain the ocean condition, and we found, well, there's no way this ocean is going to be very cold to explain the CO2 and the methane observations. And it's too hot. It's just too hot to be habitable. And we're looking to, well, what's the highest temperature microbial life on Earth can sustain? Like, what's the hottest temperature they can stay alive? And it's about the same, 400 Kelvin. So this is way too hot. So we kind of don't think this world is habitable, I would say. And that's why the press didn't like us very much, I guess. Not as much as the recent paper. But anyways, the reviewer didn't like it, so I feel like I cannot say this kind of nice things to my own paper. That's why I put what the reviewer said about the paper. So they're thinking we're adding geochemistry and connecting that to astronomy observations. But anyways, so that's kind of the state of the art. By the end of last year, we think the supercritical ocean case, pretty much we have a deep-ish atmosphere, but on the bottom we have a hydrogen water mixture that's very hot. Seems to be the best to explain what we see this Webb. Okay? But there's one thing. I'm mixing the elephant in the room, which is life. There's life. And the life situation, I would say it's not completely wrong, because the case kind of everybody really want to test here is the shallow atmosphere with the liquid water ocean. So like I said, you cannot explain the methane abundance because, if you have no life on this world that has ocean, you're going to predict 1 ppm of methane, because you can't have so much methane. There's no simultaneous to recycle it. But if you do have life, and life generates enough methane, for example, because life can do whatever. We don't know these life. For example, if this life can actually have methane outlet from the ocean or whatever, you might be able to explain the 1% methane, but that's something we actually did not look at. And we're becoming a little bit more serious about it because of this paper that was on the news about a month ago. So again, this is a spectrum that I was showing in the first two slides. So they're finding two species, DMS and DMPS, in this atmosphere of K280. Okay. Well, I have to say I'm not an astronomer because I don't do data reduction. But literally like 2 days later, after the paper, another guy called Jake Taylor, he reduced the data again. Some astronomers, they don't really think they're real, okay? Because they think the spectrum looks flat. If they wanted to be reduction, they would not claim any detection of any molecule. Okay, so I feel like we got to be a little bit cautious of the claim. But we're not. Let's not worry about that. Let's assume we do see DMS and DMPS here. What does that mean? Okay. So I guess the question is, okay, what if these molecules are there? Can we claim this to be biosignatures? Okay. By the way, if you're not familiar with like chemistry, this is the structure I've labeled all the elements for you to enjoy. All right. So I think it's okay to say that if you have an oxygen, like oxidizing atmosphere like Earth, these are pretty much valid biosignatures because in an oxidizing atmosphere, it's super easy. Once you have these molecules in the atmosphere, and like any chemistry, like if you have hydroxyl groups and an oxidizing atmosphere, it's very easy to turn them into something else. Okay, so in order to have these species out there, we pretty much have to sustain lots of them, and then lots of them are made by chemistry, like chemistry coming from life cells. So I do think it's very possible that you can claim their biosignatures for oxidized atmosphere. And I don't know if you guys see this. That's about like 4 years ago. There was a big claim they found life on Venus because they saw this gas called phosphine, PHC, in Venus atmosphere. We do not know the detection is real, but some people do. If it is there, it is weird because Venus atmosphere is very oxidized. It's a CO2 atmosphere. And it's very weird to see phosphine there because phosphine will not be able to last very long in the atmosphere. So you want to activate flux of phosphine. So it's like the same situation for DMS and DMPS. It should not exist in an oxidized atmosphere. But what if you have it in a hydrogen-rich atmosphere, right? Can we still claim these molecules to be biosignatures if we have a hydrogen atmosphere? So I'm not going to be able to answer the question right now because that's what we're working on. I don't want to say too much, not so much spoilers, but that's something we're actually working on. But whether they are or not, to be determined, I think it will really help us understand, what do we call like biosignatures? Because we're having this atmosphere that's completely different from Earth. But to me, it's like, it's quite simple to make these kind of stuff, like, seems to me, in a hydrogen atmosphere. And hydrogen doesn't really do anything to these molecules once they're formed. So I guess we have to look into this. Is where I want to end this talk with. But by the way, I want to say other than K280, there are actually other cool exoplanets out there that are in between the size of Earth and Neptune. For example, this other planet we see last year in the web of LHS 1140e. It's actually closer to Earth size. It's 1.7 Earth radii. And the temperature is actually pretty close to, the equivalent temperature is 234 Kelvin, pretty close to Earth. And we have captured spectra of it, but it's the data quality is not so great. But basically, they're claiming maybe it has a high molecular weight atmosphere. And my student had a paper last year where thinking, well, another explanation is, well, maybe it can be explained by a hydrogen atmosphere with the same surface with condensation. It can also create a flattish spectrum. And then another planet that's pretty cool that we published recently is TOI 270d. So another intermediate size exoplanet. It's a little bit harder. And we found about 1% methane, 1% CO2, and no ammonia in this planet. And then my colleague Chris Klein, I and my student were to publish on that right after the K218 paper. That's why I got a lot of press coverage. It's kind of the timing, but we think this planet is more likely to be a mini Neptune, which is a thick atmosphere world, or maybe a magma ocean world because of the no ammonia detection. But anyways, the bottom line is, I think we just got to do more observations. Pretty much we really want to understand the nature of these intermediate sized exoplanets. So for example, we want to know if they're only super Earths and mini Neptunes, like, and where's the division line? For example, we want to know, okay, does 1.5 Earth radius divide the super Earths and mini Neptunes? Or maybe it's 1.7 Earth radius. And how does the division look like? Does it look like this or that? By the way, these are just my memory drawings on the fly, no idea yet. Or maybe there's some, they belong to some new types of work which doesn't exist in the solar system. For example, these water-rich worlds, they're like these ocean planets. But the bottom line is we just need more observations of them. That's why, as lab/theory person, I started to do some observing proposals. We just really need to see more. So currently we have about 2 planets. That's in between the size of Earth and Neptune. That's kind of in the habitable temperature range. That's all we have, but we just need to observe more of them. That's why I'm putting a proposal for cycle 4 that got good rating, but very close, but didn't make it quite yet. That hopefully will fly next time. But the idea is we want to see more of them, and then hopefully we can understand this whole population of exoplanets, and that's really going to help the next generation mission to determine, hey, when you look at exoplanets, you only focus on Earth size, or maybe you can push a little bit bigger size, like maybe we can look at 1.5 Earth radius planets, and they still could be habitable, and then maybe work on Aegis eventually. Who knows? All right. So I just want to end this talk on like a very positive note. So like I know there are lots of chaotic stuff happening during this semester because of all the new changes since January 20th. But I'm just actually copying this comment from the New York Times article. So the New York Times actually reported on patriarchy and protection of life. There are lots of negative feedback, but then from the science community. But this is actually what the general public say, So it's not something that's finally done and dark anymore. It's something, they actually quite like it. It's making their day. So I'd say there are some positive things about this work that's very controversial, but I do find somebody's very happy. So yeah, so it's kind of lovely because it's kind of common. But other than that, I think I'll just finish my talk as my conclusion, advertise my lab, of course, and then I'll leave you guys if you have any questions. How do you guys feel about K2?